All right, so not only do E2 reactions have regioselectivity, they also have stereoselectivity. So let's take a look at some examples. So in this case, if we have an E2 reaction occurring here, we've got two beta hydrogens from this side and two beta hydrogens from the other side, but they're the same thing. And so you can think about the alkenes forming here. We have two options. Right, we have this trans motif, and then we have this cis motif. And as we learned, the trans motif is going to be more stable, and so this will be the major product because it forms the more stable alkene. But you can see both of them are going to be formed in this case. Let's take another look at another example. And so you can see we've got a bunch of stereochemistry going on here. We've got our base, and we're thinking about eliminating this bromine and then the beta hydrogen to it. So we're eliminating this one. And so now when we do this, we only get the trans product. Or later on, what we'll call the E product. And so it's technically not trans, but you can see the big things are on opposite sides of one another. And in this case, this is the only product, whereas before we got a mixture of the two. And so what's going on here is the mechanism of this E2 reaction. In the E2 reaction, the elimination of the hydrogen and the bromine must be in the same plane as one another, or at least approximately the same plane as one another. The reason for this is due to orbitals. So if you think about the transition state, you can probably figure it out. These sp3 orbitals must become sp2 orbitals. And in order to have that pi bond occurring, they must be in the same plane. But we won't go into great detail about that. And so if we look at the mechanism of this reaction, here we have this hydrogen and this bromine in the same plane. And so we'll just put A and B here, A and B here. And again, our base is going to come in, deprotonate through an E2 mechanism. And if we were to take a look at the Newman projection here, hydrogen would be over here, A, B. B, A. And so we can see that these two are not only in the same plane as one another, same vertical plane, but they're also anti to one another. If you try to do it this other way, this is highly likely to unoccur because there's a lot of steric hindrance, right? For your base to come in here, these two are very anti to one another, or these two are in an eclipse conformation, so it's higher energy. And so not only is it the same plane, but generally it's anti to one another. And so we can see when we're in this conformer and we think about our base removing our H and our Br, we can see that B and B are on the same side and A are on the same side. And you can see that in the same picture above, right? B is in the back of the board, B is in the back of the board, A is in the front of the board, A is in the front of the board. And so A and B will end up being on the same side as one another, right? So A and A are going to go on one side and B are going to be on the other side. And so again, anti is highly favored. And being in the same plane is required. So let's take a look at another example. Let's think about what occurs here when we add a base. And so we identify our leaving group as right here. And so what we're looking for is beta hydrogens. This carbon over here has no beta hydrogens, so it can't react over there. And then if we think over here, we have one beta hydrogen. And so in order for these two to react, they must be in the same plane and preferably anti to one another. So let's go ahead and rotate about this central bond until we get them in the same plane as one another. So one way we would do this would to imagine chlorine going in the plane and then hydrogen in the plane as well, but pointing up. And so if you think about the molecule, how we rotated that to occur, this tert butoxide group would actually come out. There'd be a hydrogen pointing in the back here. This ethyl group would be pointing out here. And then this methyl group would be going into the back of the board. And now we are free to do our E2 mechanism. And then we take a look at what stuff's on the same side. This tert butyl is on the same side as this ethyl. And then this hydrogen is on the same side as this methyl. And so our final product ends up being this. In this case, this is the only product. And so this is what we call stereospecific. You get only one product. The reaction is very specific towards one product. Whereas if we imagine this other case, right now we've gotten rid of this methyl group, and so now we have hydrogens on both sides. So we have two beta hydrogens. One of them is going to lead to the cis product. The other one is going to lead to the trans product. So here we have our trans. And then here we have our cis. If you think about it, right, we said the trans was more energetically favorable than the cis. And so this will end up being the major product. And so what we call this is being stereoselective. This means that one product is preferred from a stereochemistry perspective, right? So stereoselective means that you have a preference for one compound over the other, but you still form both. Stereospecific means that you only form one stereoisomer out of the two options. So lots to keep track of in E2 reactions. You really want to practice this stuff.